Hi guys, welcome back to Data Every Day. Today on the episode we are looking at a data set of dissolved oxygen prediction. Dissolved oxygen in water, which is this target column here. And we're going to try to predict how much dissolved oxygen there is at each one of these stations based on a bunch of these attributes. And we have a good number of features, but it looks like there's a lot of missing values. So let's get started. Let's make a new notebook. And let's call it dissolved oxygen prediction. Alright, and let's get started. Let me just import everything we need right here. I have it all ready to go. And we're also going to need logistic regression. Okay, so we're going to use NumPy and pandas as usual, and we're not going to need any label encoding this time, just a standard scalar and train test split function. And we're going to use two models. One, we're going to try logistic regression, which will be a classic regression problem, and then, linear regression, classic regression problem, and then we will try doing classification with logistic regression after it's done. So let's get started and then take a look at our data. So let's read it in with the pandas.readCSV function. And we can get the file right over here. We'll be using train. I forgot to import. And we can look right off the bat. Let's get some preliminary information. We have a lot of missing values, right? There's 147 rows total. And in many of these, there's only 30 or so non-null values, so all the rest are null. So let's start pre-processing it. And I will make a new section here just for the missing values. And let's check all of the columns that have missing values and the counts in each one. And you can see they follow a sort of predictable pattern. There's some columns with very few and other columns with a huge amount, right? Because we only have 147 total entries, right? So having 115 missing values makes the column practically useless. So let's see if we let's get a list of all the columns that have over 100 missing values. So to do that, we can say data.isNA.sum, which is just this list here, over 100. And that should give us true false, where false will be if it's below 100, and true if it's above 100, right? And so from there, this thing, we can index this. We can index the columns at this. So all these trues, we'll get the column names for everything that's true, and that will be that. Oh, what happened? Oh, did I not? Wait, what's the matter here? 1 second. I don't see what the problem will be here. Oh, it worked. Oh, I had a... Okay, in either case it's working. Now let's just turn that to a list, since it's currently an index object. And now we have a list of all of the columns that have over 100 missing values. See O23 is there, but O22 is not, right? Alright, let's save that in a variable called no columns, and we're just going to drop no columns. Data.drop no columns. So from the first the column axis and in place. Alright, now if we take a look at our data again, we should have fewer features, only 12 now, but we have much fewer missing values, and we can check. Let's check actually, since we can't visualize this very well, we want to know where are the missing values that remain. Well, first of all, how many more do we have? It says there's 2 in each column, right? But we don't know, are those the same rows? Are there 2 rows that have all the missing values? Or are there many different rows and the missing values are scattered among rows? Because that will depend on how we want to deal with this. If it's true that there's only just 2 rows in there that have missing values, it'd be safe to drop those rows. But if the values are scattered, we're going to have to impute them using the means of the columns. So we can check how many rows have missing values and how many columns have missing values. So for the columns, we'll get this thing, right? And then let's specify axis 0. This is the same thing as what we have here, right? Because it's summing over the rows, so we get all the counts in the columns. But this is just to distinguish, so you can understand we're distinguishing from the rows that we're about to do. Not equals 0. So this will give us trues in any of the places where there's not 0, right? So the first 2 are false, the rest is true. And if we sum across that, we get the total number of columns with missing values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Now if we do the same thing except along axis 1, which is the columns, so now we're summing across the columns, we'll get the rows with missing values. Oh. So we can't actually visualize it right now because there's this dot dot dot. There's at least some in there, we know. So let's try this again. Not equals 0. I'll put in here. And we can't see, but if we sum across that, we now get the number of missing values in the number of rows with missing values. So let's just condense this. Let's just put this up here, and then I actually have, just to save time, I included these labels, and you can see, so columns with missing values 10, rows with missing values 3. Alright, so because we only have 3 rows with missing values, we can just drop them, right? We can drop them, and our total number of examples will go from 147 to 144. So data.dropNA, which just drops null values along a specified axis. We're going to choose the 0 axis, so we're dropping rows in place true. And all that does now, if we check the total number, and I'm going to sum twice so that we get the total number of NA values in the matrix, we have 0. There's nothing left. So now our data is fully free of null values. And let's just take another look at it before we do anything else. We gotta see what we have to do next. Well, we have fully numerical data, so we have no need to encode anything. In that case, we can move on to splitting and scaling. So we're going to split our data into x and y. So y will be the target column. Oh, actually, you know what I noticed? This ID column, not helping us. We already have indexes. We're not submitting this for any sort of competition or anything, so we don't have to retain which ID is which. This is the training set anyway. Let's just drop this ID column. So we can do this right. Let's just do it right here. Okay. Data.drop ID axis 1 in place true. Okay. Now look at data again. Okay, now we're going to take the target column off, and we're going to make x everything except the target column. Now y is just this column, the target column, and x is everything else. Alright, and we're going to create a scalar object. Remember at the top I imported the standard scalar from sklearn. Scalar is going to be standard scalar. And x is going to be scalar.fitTransformX. And that's basically just going to take is going to fit the scalar to the data right here, which means it's going to take each column and calculate how can it squish it so that the whole column has univariance. And then every single column is going to have univariance so that most of the values fall between -1 and 1. We're going to do that for every column, and then we're going to transform x, which just applies the transformation, and then we're going to store it back in x. Alright, now if I want to look at x again, I should turn it, fit transform actually returns a numpy array. So if we turn it back into a data frame, we can get a nicer look at it. You can see everything has been scaled with, so that has mean 0 and univariance. Alright, so I think we're ready to train, right? So let's make a new one. And this is going to be regression. So our model will be linear regression, which I imported from sklearn. And we're going to fit it. Aha, right. We've got to split our data first. Xtrain, xtest, ytrain, ytest, train test split, xy, and a train size of 70%. Okay, now we're going to fit it on the xtrain, ytrain, and let's say model r squared, r2 equals model.score xtest ytest. So this will return the r squared value, r squared score for our models fit. And this is linear regression. And we can just print it out down here. Print model r squared score model r2. Alright, and we did not do that great, right? I mean, it looks like maybe we need some more information. I don't know if the data set is so predictive of this, but 0.44, you know, it's not so fair to say how good this is, because we're not really sure how the problem, what the ceiling of the performance is. But let's say, okay, maybe I could change the problem a little. Let's try this. New problem. Predicting high or low dissolved oxygen. Alright, so this was predicting the levels of dissolved oxygen in rivers, river water, right? But now let's say, okay, let's change the problem a little. Let's try to predict just if the, let's turn it into a classification problem. Is the level of dissolved oxygen high or low? That's 0 or 1. That's just very simple. And this will just allow us to perhaps get a better accuracy at a simpler problem. Better performance, I should say. So if we look at y, which is our target column, this is a continuous variable, right? Let's bin it. Let's turn it into two discrete values, 0 or 1. So we're going to discretize this variable, and let's look at the mean. We're going to do it in terms of the distribution of the variable. So the mean is 9.1. So what that means is anything over 9.1 we're going to set to 1, and anything under 9.1 we're going to set to 0. Right? So let's make a variable called ynew. This will be the pandas.qcut function. Now before I start in a variable, I'll show you what it does. If you don't know, it takes y, takes a number of bins, here too, because we're just doing 0 and 1, and we'll give it some labels, 0, 1. And it's just going to take those continuous values and bin them, right? And it says down here 0 is less than 1. If we had done 4, it will, must be, right, I have to specify this, 2, 3, 3. Oh my. And now it will split them into 0, 1, 2, 3. And that will be quantile based, right? So it will be the right. You understand? Let's just change it back though, because we're just going to do 0 and 1. And why don't we try training a new model now, but this time it will be a classification model. So our model is going to be logistic regression, and before that, let's split it once more, so we can just use the same variables here. It's not that bad. So y train, x train, x test, y train, y test equals train test split, and I'm just going to save this guy in y new. So x y new with the same train size, and then we're going to fit the logistic regression model to this new classification data. So x train, y train, and then model accuracy we'll say is model.score. So classification model will return accuracy value from score, whereas the regression model will return a r-squared value from score. So here x test, y test, and then let's just print it out, model accuracy, model ac. And we have a, I'd say, better performing model, right? Well, it's a simpler problem, but it did better. It's almost 70% accuracy in classifying whether or not the dissolved oxygen content will be high or low depending on these rest of features, right? Alright, I think that sums it up for today. Thanks so much for watching. If you enjoyed the video, make sure to subscribe and hit the bell, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a great day.